Okay, so let's look at problem 8 from the exam. So this was the true-false. So let me actually put this up here so we can see the questions. So you can see the answers also, but I'll try to go through and explain why we get these. So the first one, we're told if a function is continuous, then it's differentiable, and this is a false statement. So as an example, we can look at something like the absolute value function. So this function looks like this. It has this sharp corner at 0, so it's continuous. There are no jumps or gaps in the graph, but it's not differentiable at x equals 1, or sorry, x equals 0. And you more or less showed this earlier in the exam. It was a very similar problem to that. Okay, so now let's look at problem B. We're told if f of x is equal to 3x cubed, then log of y is a linear function of log of x. So this is a true statement. This is basically saying that if you have a power function like this, then the log-log plot will be linear. So let's see how that works. So we have y equals 3x cubed. If we take the log of both sides, we get log of y is equal to log of 3x cubed. And we can simplify this to log of 3 plus log of x cubed. And then we can simplify that a bit further to log of 3 plus 3 log of x. So we can see that log of y is a linear function of log of x, where log of 3 is the y-intercept, and this 3 is the slope. Alright, let's look at C. So C says that if f is a differentiable function and f prime has 3 zeros between 1 and 2, then f of x has at most 4 zeros on that interval. And this is true by Rolle's theorem. By the way, I should maybe, I guess, say that this last one was true. So C is false by Rolle's theorem. So Rolle's theorem says if f is differentiable, then f prime of x has at least 1 zero. Wait, what am I saying? True by Rolle's theorem. So if f is differentiable, then f prime of x has at least 1 zero between every 2 zeros of f of x. So give me 2 zeros of the original function. F prime must have at least 1 zero in between them. So if f had more than 4 zeros, this would imply f prime has more than 3 zeros, because between every 2 of these zeros, f prime must have had at least 1. So let's say there were 5 zeros, then we would have a 0 of f prime here in between the first pair, a 0 in between the second pair, a 0 in between the third pair, and a 0 in between the fourth pair, so there would be 4 zeros of the derivative. So that would be contradictory to the information that was given to us in the problem that the derivative only had 3 zeros. So that means that the function can only have up to 4 zeros. Okay, so let's look at D now. So D says if f of 5 equals 3 and f of 7 equals -2, then f of x equals 0 for at least one value of x in that interval. So this looks like the setup for the intermediate value theorem, but there's a key assumption that's missing. Specifically, the intermediate value theorem is only true if the function is continuous. So since we're not told that, it's false. And so what you can have is a graph which looks something like this. So let's see, it was f of 5 is equal to 3, and f of 7 is equal to -2, but we could have a function which does something like this and never actually hits a 0. So that's why that's false. So now let's look at the last problem. So we're given some values of f, and it looks like as we plug in values of f closer to 0, the values of the output are getting closer to 1. And we're asked if we can conclude that limit as x goes to 0, f of x is equal to 1. And this is false because if we look at these values, we're told about 0.1, 0.01, 0.001, 0.0001. We're only told information about value right side of 0. So this is false because we know nothing about the limit as x approaches 0 from the left of this function. Also, we don't know for sure that limit as x approaches 0 from the right, f of x is equal to 1. Because we're only given some values at a set number of points, we're not given a formula for f, so we really don't know what happens. For example, between 0 and 0.0001, the function might go crazy and go up to like 17 or something like that and not be anywhere close to 1, even though it looks like it's getting closer to 1. So basically, the main problem, I think, is that the limit from the left we know nothing about, but even more so, we're not even 100% sure that the limit from the right is equal to 1. So therefore, we definitely can't conclude anything about the full limit.